Hello, this video is an introduction to the conditional proof. I made another video on the indirect proofs, and this video more or less assumes that you've watched that video, and it more or less assumes that you are familiar with how to do proofs and propositional logic. You are familiar with the rules of inference and replacement. You know what you're looking at right here. And if it wasn't for the conditional proof, you could feel pretty confident in getting the right solution. The goal of this video is just to introduce this new concept called the conditional proof. Now, the conditional proof works very similarly to the indirect proof. I'm going to be able to show you a little example, kind of an abstract version of the argument here. So with the indirect proofs, what we were able to do is we indented, drew a vertical line, and then we assumed the opposite of our conclusion. With a conditional proof, you're doing something else. So what you're always aiming at in a conditional proof is, this is going to be a big surprise, you're always aiming at a conditional in a conditional proof. So let's pretend we're aiming to prove that if C is true, then P is true. The thing you assume on the first line of your conditional proof is the antecedent of the conditional. So we'll assume C, and then we simply write A, C, P, assumption for a conditional proof. And then, utilizing whatever other premises we have in all of our rules, we try to go step by step until we get to the consequent, or P. And if we can do this, what we have shown is that if C is true, then P necessarily follows. Or every time C is true, P must also be true. You haven't proven that C is true. All you're saying is that if C is true, then P is true. So if we've proven that, no matter how many steps it takes, then we're going to say this is premise N. Then we have proven that if C is true, then P is true. And we know that from lines 4 through n-1, I'm trying to be a mathematician here, by a conditional proof. And that's how it would go. It's easier, in a sense, it's easier to leave the assumption in a conditional proof than with a indirect proof. Because with an indirect proof, if you assume not C, you have to stay in that proof until you get a logical contradiction, and then you can assert the opposite of what you first assumed. Here, in a conditional proof, no matter what you start off with, we're going to pretend like we start off with the assumption not C here too. Where if you were, we might say that P is where it makes the most sense to go, but if you got to say not C and J some weird way, then you could still assume not C, therefore not C and J. I'm only showing you this to show you the flexibility of the conditional proof. That you can leave it whenever you want to, and when you do leave it, you will use your last step as your consequent. Okay, so we have that. Let us now try to solve this problem. And looking at it, I didn't bother to solve the problem before making this video because that wouldn't be very much fun. So let's try to solve this problem. Our conclusion is not a conditional. In many of these example problems, you will see that in a conditional, in the problems designed to be a conditional, you'll see that the conclusion is itself written as a conditional. So we're going to have to try to figure out what this might be saying. So let's look at this argument. And I know you can actually solve this one without a conditional or indirect proof, but we're going to make it interesting and useful here. So we're going to try to solve it with the conditional proof. So why don't you pause the video? I'm going to pause the video and see if you can figure out what the next step might be. Okay, I still don't see the solution, but I think I have a clue. All right, so I'm going to implement this strategy, and when we're looking at this, we're trying to get to a T, and I see the only place that a t is found is here on premise 2, s and t, which means that probably at some point I'm going to have to use modus ponens on step 2. Now, step 2, the antecedent here is if p then r. How do I get if p then r? Well, this kind of looks tricky. This seems like a case for the conditional proof. So I'm going to start off, I'm going to try to prove if p then r. So that's my goal. I'm going to just write this on the side so I can remember what my bullseye is. I'm going to assume p. And I'm going to say I know that. Well, I don't know it, but I'm going to say that it's an assumption for a conditional proof. Okay? Then step 5, now we can start to move along a little bit. If p is true, then I can apply that to step 1, and I can get q or r. And I know that from 1, 4, modus ponens. All right. Now 6, look at step 6. I'm going to make this a little bit neater. Q or R, that doesn't fit in nicely with step 3, but I think I can manipulate it so that it does. So we can do this one of two ways. And you can probably see them already. That number 3 says if Q is true, then R is true. I'm going to use implication. So I'm going to get not Q or R from 3 imp. Now that I have that, I'm going to get, no, maybe that was the wrong move. So for some reason I thought, this happens when you're doing logic sometimes, at least I find it's true, that your mind kind of snags up. For some reason I thought that when I waved the wand of implication on premise 3, I was going to get a conjunction, then I could simplify the not Q, but obviously that's not what happens when you use implication. You get a disjunction. So I wonder what else I could do. I could erase it, but we know it's true, so I might as well keep it up there. This is what I'm going to do. I'm just going to try some things. I'm actually going to throw a double negation onto 5, so I'm going to get not Q or R. So that's 5 double negation. Then I'm going to use implication to get not Q, therefore R. And that is from 7 implication. Then I'm going to use transposition, which will give me not R, therefore Q. I'm cheating just a touch with the double negations. I should either add a negation on both or subtract a negation on both. But, you know, it doesn't affect the problem. Now with double negation. And now I have this. I have 3 says if Q then R. This says not R, therefore Q. So I can use 9 and 3 together for hypothetical syllogism. Then I'm going to use implication again, not R or R. This is from 10 imp. Then 12 double negation on 11. Then 13 I'm going to use tautology on step 12. Now we did what we wanted to do. We have if P, that shows us R is true. So now we can leave the assumption, and I put line 4 is my antecedent, and I put line 13 as my consequent. And I say that's from step 4 through 13, conditional proof. Now I can use step 2 finally. And between 2 and 14, I can use modus ponens. 2, 14, modus ponens. 16, we simplify T and get 15 from 15 simplification. That's our conclusion, and that's how it's done. All right, so that was the basics of a conditional proof. And in the next video, we're going to go through a much more complicated problem together. Thank you.